Hello, everyone. Thanks so much for dialing in today. The Center for Petroleum and Geosystems Engineering is happy to have you joining us for our first Knowledge Pipeline webinar series. Today's topic is Induced Seismicity. The Knowledge Pipeline series is put together for our alumni and colleagues, emphasizing the interdisciplinary nature of the cutting-edge research done by the Center for Petroleum and Geosystems Engineering. I'm Mark McClure, and it's my pleasure to host this webinar today. I'm an assistant professor in the Department of Petroleum and Geosystems Engineering at the University of Texas at Austin. One of my areas of specialization is induced seismicity. We don't normally expect issues with audio, but if you should lose sound, our suggestion is that you exit the webinar, close down your browser, and then re-enter. If you signed up to receive CEU credits for attending this webinar today, you will need to verify your participation by clicking on the URL shown at the end of this presentation after the Q&A session. This will be your only opportunity to click on the link. We will have an opportunity for discussion and questions at the end of the presentation today. I'm going to be tracking questions from our audience throughout the webinar. Look for the chat function at the left-hand side of your screen. You can type your questions there, and we will address them at the end of the presentation. The webinar will end at 1 p.m. Now I'd like to introduce our presenters for today, Drs. Cliff Frohlich and Jon Olson. They will be presenting on Induced Seismicity, a multidisciplinary perspective. Dr. Cliff Frohlich was born in Wisconsin, grew up in Ohio, South Dakota, and Maryland, attended Rennell College in Iowa, where he received a BA in mathematics and physics, and then went on to graduate school in New York, where he received a PhD in physics from Cornell University. Since 1978, he's been a researcher at the University of Texas Institute for Geophysics, where he now serves as associate director. Dr. Frohlich is a seismologist with an interest in deep earthquakes, Texas earthquakes, induced seismicity, moonquakes, and the statistical analysis of earthquake catalogs. Welcome, Cliff. Dr. Jon Olson, a native of Minnesota, attended the University of Notre Dame, where he received a BS in civil engineering and a BS in earth sciences. His PhD in applied earth sciences is from Stanford University. Prior to becoming a professor at the University of Texas at Austin in the Department of Petroleum and Geosystems Engineering, Dr. Olson worked for Mobil Oil Company's research lab. At the university, Dr. Olson's research focuses on production optimization and environmental impact issues related to hydraulic fracturing and unconventional oil and gas development. These include induced seismicity, physical and numerical modeling of hydraulic fracture propagation, interaction of hydraulic fractures with natural fractures, wellbore stability, reservoir compaction and subsidence, and natural fracture characterization. Welcome, Jon. With those introductions complete, I will turn it over to Cliff and Jon to get it.
Okay, thanks, Mark. My name is Cliff Frohlich, and I'm going to start the presentation on induced seismicity, that is, earthquakes that are probably caused by human activities, and then Jon will finish up. In today's presentation, I'm going to give some background on the history of induced seismicity. Then I'm going to talk about two examples briefly, earthquakes in Oklahoma, and then more detail about a sequence in Dallas-Fort Worth in 2008 and 2009. I'm going to give some more information about things you might want to know if you found yourself in a position to set policy or craft regulations. I'm going to talk about traffic light systems. And then finally, Jon is going to talk about various aspects of mechanics of induced earthquakes. Concerning the history, earthquake scientists first realized that humans could cause earthquakes when they were building Hoover Dam in the 1930s and filling Lake Mead. And they started filling the lake in 1935. People first started feeling earthquakes in 1936. In 1939, there was a magnitude 5. There were thousands of quakes recorded, and people noticed that the rate of seismic activity fluctuated as the lake levels fluctuated. The next major event in the history happened in the Denver area. The Army had a waste disposal well at a institution called the Rocky Mountain Arsenal, and they had injected some 100 million gallons of toxic waste into this well, which is 3.6 kilometers deep near Denver. Now, no one's ever said exactly what they were injecting, but the word on the street is that it was things related to the manufacture of nerve gas. Anyway, they began injecting in March of 1962. People began feeling earthquakes in April of 1962, and a geologist named David Evans noticed that the seismicity rate was related to the injection rate, more injection, more earthquakes. The Army stopped injecting in 1966. However, the earthquakes continued That is, the largest earthquakes of magnitude 5.3 and 5.2 occurred in 1967. So in the science community, it's been established for more than 50 years that humans sometimes do induce or trigger earthquakes. They can do this when you're impounding lakes or reservoir, if they're deep enough, a couple hundred meters or so. They can do it when they're injecting waste fluids into deep wells. Other kinds of fluid injection, like water flooding to enhance petroleum production, geothermal operations, and sometimes even CO2 injection. Sometimes earthquakes are induced when you extract fluids, that is, when you are producing oil or natural gas. And sometimes people make the distinction between induced and triggered earthquakes. And when they make this distinction, an induced earthquake is where the human activity actually changes the underground stress. For example, when you fill a lake, the weight of the water increases the stress on a fault beneath it, and so that could induce an earthquake. However, when you speak of a triggered earthquake, this is where the human activity isn't affecting the stress. That is, it's changing the friction on stuck faults. And so the earthquakes are a product of natural tectonic stresses, but the human activity is changing the friction, allowing the earthquake to occur. Now, I'm going to talk about Oklahoma. This is not a very good map, but the map shows Midwestern United States from Texas to North Dakota, and the dots are earthquakes. And the plot shows the number of earthquakes versus time. It's from 1965 to about 2000. What we see is the line is straight, meaning there's about 20 earthquakes per year in the Midwest. Then in the early 2000s, the earthquakes happened more quickly, and then finally in 2010 they happened more quickly still. And especially in Oklahoma, many people believe that this increase in earthquakes beginning in the early 2000s is related to earthquakes caused by wastewater injection in disposal wells, especially in Oklahoma. Here's a map of Oklahoma. And it shows the earthquakes that were recorded from over a 2-year period from November 2009 to November 2011. There's 48 earthquakes. This is considerably more earthquakes than had happened in previous times. But then from 2011 to 2013, we have even more earthquakes occurring in Oklahoma. That is, there's almost 2,000 earthquakes on this map during that period. And again, most people believe that at least the majority of these earthquakes are related to increased fluid injection to dispose of waste fluids related to petroleum production. Well, one of the earthquakes in the 2011 had a magnitude 5.6, which is no joke. In fact, that may be the largest earthquake anywhere in the world caused by fluid injection. That earthquake did cause some damage, although the damage was quite localized. And these earthquakes have continued. On this map are earthquakes in Oklahoma over the 30-day interval from mid-September to mid-October of this year. Now I'm going to talk about a sequence of earthquakes that happened near Dallas-Fort Worth in 2008 and 2009. In fact, on Halloween night in 2008, there were several earthquakes that occurred. On the map here, we have a Dallas County on the right, where the town or city of Dallas is, and Fort Worth is in Tarrant County. This is 10 kilometers. The red circles are earthquakes that the U.S. Geological Survey located in 2008. The black triangles on this map are temporary seismograph stations that some colleagues of mine at Southern Methodist University installed after the first quakes were felt. And using these temporary stations, we located aftershocks, and all the aftershocks we located in this 1 kilometer yellow square. Now, almost certainly the red earthquakes that reported by the USGS also occurred within this square. So one thing that this map illustrates is when you don't have regional stations set up, that typically for little earthquakes, magnitude 2s and 3s, you're going to get location errors of 5 to 15 kilometers. And in my talk, when we have asterisks in green, these are things you might want to remember about this if you find yourself falling asleep. One when I was a graduate student and you located earthquakes, the first thing you do is run to a map. However, we've come a long ways from then, so now what you do is you run to Google Maps. And if you run to Google Maps for that little square, what you find is this. Here the red are where we located the earthquakes along sort of a 1 kilometer line. And there's this facility here, which turns out to be an injection disposal well. When I first saw this, I didn't know where this area was. And so if you back off on Google Map, the area in the last slide is down here at the bottom. This is the Dallas-Fort Worth Airport. Here's a runway. Here's a runway. And so the earthquakes that we located in 2008 were on the Dallas-Fort Worth Airport down here near this injection disposal well. The next slide is a map. This is the same area. This is one of the runways. This is another runway. Here the yellow triangles are the earthquakes that we located. The white-red symbols are producing natural gas wells. The white and red are tops and bottoms of the well. And the blue is an injection disposal well operated by Chesapeake Energy. And what you notice is that our locations for the earthquakes are very close to the injection disposal well. Our preferred focal depths were about 4.5 kilometers, whereas the injection disposal well was injecting at a depth of about 4 kilometers. And another thing you notice is that the earthquakes were not near the producing wells that had been fracked. And finally, I'd like to make a point again that the only way we were able to get accurate in depths and locations for these earthquakes was because we had data from the dense local seismograph network. We couldn't get accurate depths or locations using USGS information alone. Now to schematically show what's going on, this is a cross-section of the geology. There's the Dallas-Fort Worth Metroplex, and the oil and gas is being produced from a strata called the Barnett Shale. And there's there's gas in the Barnett Shale, but the Barnett Shale is very impermeable, so if you drilled a well down there, not much gas would flow out. But if you frack the shale, that is, you let off essentially an explosion in the shale, that increases the permeability, and it allows the gas to flow. And in fact, one thing that is a technological improvement in the last 20 years is people are very good at drilling down and doing horizontal drilling. So in an area like Dallas, where you don't want to put an oil rig everywhere, you can drill down and then go sideways, so you can frack large areas of the shale from a single well. Now, when you produce the gas, along with the gas, you also produce some of the frack water, which comes back, and sometimes water that's just in the strata. So you have to dispose of that. In the Barnett situation, it's convenient to dispose of it in the Ellenberger, because although the Barnett shale is very impermeable, the Ellenberger is very permeable, so you can pump lots of water in there. And the fact that you have the impermeable Barnett above it makes it convenient for injection disposal, because the water in the Ellenberger won't get back to the surface. Now, what does a frack job look like? And here's a air photo of a frack job. You notice that there's trucks with natural gas and water. There's a pond for storing frack fluid when it comes back. This is the way things are. Now, is this a good thing for you? Well, suppose you live over in this house here. If you have the mineral rights, all this activity in these trucks is just going, you can just hear that money rumbling on its way to the bank. On the other hand, if you live over here at this house and you don't have the mineral rights, it's very inconvenient to have these trucks running down your kids on the way to school and causing all this noise and messing with your roads. Now, it turns out there is a great many injection wells in Texas in the United States, and some of these have been in use since the 1930s. Here's a map of Texas, and the circles are earthquakes. The green circles are almost certainly natural earthquakes because they aren't near any oil and gas fields or injection wells, so they would have to be natural. The red circles might be natural, or they might be caused by humans because they are near, in this case, the yellow squares are injection wells. As I said, there's tens of thousands of injection wells, some of these used since the 1930s. Almost all the earthquakes in Texas are very, very small, and they're quite rare. So one thing you get from this picture is that if a waste disposal by injection was hugely dangerous, we would certainly know, because Texas would be famous as a state that was just rocked by big earthquakes all the time. In fact, most people in Texas don't know there are any earthquakes. So for the most part, this is quite safe. Now, Texas is not the only state with injection wells. Here's a map. You see that Texas has more injection wells than other states, but there's other states that have a lot. Oklahoma, Kansas, California. The use of deep wells to get rid of fluids is common and throughout Texas, throughout the United States and much of the world. Now, you might say that was an awful lot of injection wells on the map of Texas. Where are these things? And here's a picture. The track here is the Texas Motor Speedway west of Dallas. And this is pictures taken from an airplane. Each one of these white areas with these white things is a frac pad. And so you can see there's just frac pads everywhere, like a pincushion. On the other hand, when you drive on the highway here, you don't see them. But there's parts of the country when you fly over, you'll see all these frac pads almost everywhere. Okay, now let's back up a minute and ask, when might fluid injection cause earthquakes? The process of producing natural gas from tight gas shales like the Barnett Shale involves 4 steps. You have to drill a well. You have to frack the well to increase the permeability so the gas will flow out. You have to extract the gas, and when you do that, you'll get some frac fluid and other fluids back. And then the fluids that you don't want, you have to dispose of in an injection disposal well. Now, it turns out that I'm unaware of anybody who ever caused an earthquake simply by drilling a well. Never happens. Fracking wells, it turns out that only very rarely will fracking a well cause an earthquake big enough for anyone to feel, say, magnitude 2. A few years ago, I would say it never happens, but there have been a few situations where people fracked wells and they had earthquakes as big as 2 or 3, but it's still very rare. Extracting oil and gas sometimes causes earthquakes. However, where this happens, it's usually in situations where they've been extracting huge amounts of oil and gas from decades. And in fact, in situations where, like the fracking, where you have individual wells, it's very rare that extracting oil and gas causes earthquakes. However, injection, when you're disposing of fluids, as we mentioned, sometimes does cause earthquakes. But the thing I want to remember is that the hydrofracking almost never causes true earthquakes bigger than, say, magnitude 1.5 or 2. Now, you can't believe how many times I've explained this to media people, and they say, okay, so drilling and fracking causes earthquakes, right? And the reason they say this is because they're using drilling or fracking as a generic term for this whole 4-step process. In fact, no, it isn't the drilling or the fracking that's the problem. It's usually the fluid disposal. And of course, companies hate it when you say drilling or fracking causes quakes, because if it did, it would really interfere with producing oil and gas. When it's the disposal, the company has options. You can, if you're disposing in a well that causes earthquakes, you can find a different well, or you could even treat the fluid like we do sewage in other ways. So it's not the fracking, it's the disposal. Now, I'm going to shift gears and talk about a couple matters of policy. There's 2 sort of approaches that governments use to regulate induced earthquakes related to injection. One is case-by-case regulation, whereas after an earthquake occurs, a government may shut down injection and impose strict rules that operators must follow to continue production or injection. The second kind is called a traffic light system. That is, before an earthquake occurs, there are rules set up that when certain magnitudes or ground motion levels happen, that they have to respond. That is, green is business as usual, but say when a magnitude 2.6 happens, you have to, say, reduce the injection pressures, and then a magnitude 3 or 4, for example, they had to shut down operations. Now, in terms of case-by-case regulation, the advantage is that a government responds to a potential crisis situation and protects the public. The application of the rule may depend on population density and other issues on a case-by-case basis. The disadvantage is that often governments respond to political pressure and they may stop an industrial operation in situations of minimal danger to the public. The rules are sometimes crafted quickly and often are completely unrealistic. Rule makers are sometimes poorly informed and they have very low tolerance for earthquakes. And finally, there are huge geographic differences in how induced earthquakes behave, and the rules seldom account for this. Now, what people would like is what I call a silver bullet. And that would be a simple result about injection-induced earthquakes that would make it straightforward to manage injection and avoid hazard. And when I was a kid, it was the Lone Ranger. He used silver bullets to maintain the frontier. I see this picture, though, as two seismologists who were about to try apply a silver bullet to manage injection and avoid earthquake hazard. The problem is that so far we haven't yet found a silver bullet, as we don't know how to do this, and it's possible, considering the differences in each various areas, that we may not find a silver bullet. Now, the second category for managing induced earthquakes is the traffic light system. Again, before an earthquake occurs, there are rules set up concerning how to respond. If a certain magnitude is reached, then the injection is shut off. The advantage is this provides a clear administrative solution for both the field operator and the government regulator concerning the well operations. One disadvantage, however, is that if you have a red light, how do you get back to green? A traffic light on the way to work wouldn't be very good if every time it turned red, you were stopped for the rest of the day or the week. Finally, the record shows that often the largest quakes may occur months or even years after the red light happens. And finally, what's called monitoring is problematic. Determining the location and magnitude is not straightforward and subject to disagreement. Remember the Dallas-Fort Worth situation where the USGS locations were 5 to 15 kilometers different from our locations. Magnitudes are not a precise statistic either. For an earthquake that occurred in East Texas in May of 2012, these were the magnitudes reported. The NEIC, which is the USGS, reported 3 different magnitudes from 4.4 to 4.8 using different scales. The International Data Center reported no fewer than 8 magnitudes. And so what we see is that the magnitudes were reported between 4.2 and 5.5. So if you're going to have a traffic light system, you need to define very clearly whose magnitude you're using and whose location you're using. I'll quickly give 2 examples. In El Salvador, there was a geothermal field in an area called Berlin. Large earthquakes do occur in El Salvador. There was, for example, a magnitude 7.4 last month. In 2002, they implemented a traffic light system. The traffic light always stayed green, so the field is continued to operate. And this is used as the poster child for a traffic light system that works, mainly because the traffic light never turned red. On the other hand, the bad boy of traffic light systems is a geothermal project in Basel, Switzerland. This was a $1 billion geothermal project beneath Basel. They had a very low red threshold. A magnitude 2.6 tripped yellow. They reduced pressures. Then a magnitude 3.4 earthquake happened, shutting down the field. There were thousands of damage claims processed by the insurer, and the $1 billion field never produced any energy. It's a little strange in this retrospect that they use a traffic light system here because a magnitude 6.5 had occurred in Basel in 650 years ago, and magnitude 3s were fairly common. And I can see I've used up my time.
Okay, thank you, Cliff.
I'm going to turn this over to John.
And I just want to remind you that if you have any questions, please don't forget to type them in the little chat box on the left-hand side of the screen. So to start with, what I'd like to do, and this kind of summarizes some of what Cliff said, but transitions into the mechanical aspect of the problem. There's a report that the National Research Council published in 2013 on induced seismicity. And this is something basically Congress was asking the National Academies of Science and Engineering to study this problem because it had become significant in the public eye. And one of the things that, well, these are a summary of the main conclusions of that study, and one of the things they said was that basic processes are well understood. So from the mechanical standpoint, we know how, for instance, injection wells and other kinds of things can cause earthquakes, but prediction is still elusive, and I'll talk a little bit more about that as we go through. The other thing to remember is that only a very small fraction of almost 1 million active wells in the United States have had anything to do with induced felt earthquakes. Finally, the report says hydraulic fracturing, as Cliff had said, as it's currently practiced, really does not pose a high risk for inducing felt seismic events. Processes that balance injection and withdrawal, things like enhanced oil recovery, water flooding, things like that, are thought to be much lower risk. The things that they singled out as potential risk, and they didn't say high risk, they just said some risk, are depletion, which would be production, or continuous injection of wastewater. But still, even for the wastewater case, as Cliff said, there are very few events associated with the over 30,000 Class II injection wells that are located in the United States. Finally, they did comment, since this is a potential for the future, CCS, which is carbon capture and storage, may have a potential for inducing larger seismic events, and that's because, like wastewater injection, it's long-term injection of large volumes. So let's talk a little bit about the mechanics. To introduce this, I just want to remind you the way we look at stress in the subsurface is there are essentially 3 principal directions of stress. And if you look at the diagram on the left-hand side of the screen, essentially we have the vertical stress and 2 horizontal stresses. And the horizontal stresses we divide into a maximum and minimum depending on their magnitude. Now these stresses are where our impetus for failure occurs, things that could cause fault slip and earthquakes. So if we look at rock failure modes, if you look at the slide I have now, if we concentrate on the left-hand side, if we were to take a core sample, a 1-inch diameter core sample, and stick it in the laboratory and apply a vertical stress to it, eventually it would break, and that failure in an unconfined test would be largely tensile failure. The rock would break apart, there'd be a little bit of shear. In the subsurface, it's a little bit different because essentially we have the rock around the rock around our sample would be exerting support, and so that we call that the confining stress. And then when we apply a vertical stress, we often see a more controlled failure. So the failure could look like, in the case of a vertical stress being the maximum stress, we would get something that would look like a fault that would slip like this, and we would call that a normal fault. So the fault is oblique to the maximum stress direction, which would be the red arrows here. If we roll this over on its side, or excuse me, the other thing we can do in this case, based on the magnitudes of the stresses, is other things that can happen that would cause failure would be hydraulic fracturing. So Cliff was talking a little bit about hydraulic fracturing. How do we tell whether we get the shear failure, which is the faulting, versus hydraulic fracturing? Oftentimes it has to do with the rate of injection and the pressure of injection. So the 2 bullet slides at the top say slower injection below frac gradient, which is what we typically do in injection wells, can induce shear failure. If we're doing a frac job, we're injecting at much higher rate, and that essentially gives us the hydraulic fracture behavior. Now this is for a normal faulting stress regime, which is what we call the kind of stress when the vertical stress is the most compressive stress. In some areas of the Earth, the most compressive stress is actually the horizontal stress. And so now I've rotated this diagram by 90 degrees. SH max is what we would call that red stress. The vertical stress would be the smaller arrows, and the faulting we would get now would be a thrust fault instead of a normal fault. Both of these things are the types of faults that we can find in oil fields. In this particular case, where the vertical stress is the minimum stress, our hydraulic fracture would not be vertical anymore, it would be horizontal. And typically we don't hydraulically fracture in those kinds of environments. So what do these faults look like in the field? So if you look at this diagram here, this is from the Bristol Channel in England, and this is a fault that has a meter scale slip. You can see these layers out there. These are all carbonate layers. The fault plane itself is that planar feature that's going off into the distance to the left of the man standing on the hanging wall. And the hanging wall is, for a normal fault, is the wall that's going to go down. The footwall is on the other side of the fault. You can see a bedding plane which has been offset That yellow arrow indicates the slip vector, and you can see it's on the order of maybe 1 to 2 meters of slip of offset on this particular fault. And it's a normal fault in scale, but this is a meter scale slip on the fault. Here's a thrust fault with a similar scale of slip. You can see a geologist standing there with his hand on the fault for scale, and the slip here basically is the hanging wall or the block above the fault has actually moved up in this case. We can find other examples of faults where the scale of slip is smaller. Here's some examples from the coast in California of the Monterey Formation, which is sometimes an example of a shale, unconventional shale type production, although it's got a lot of other lithologies in it too. But you can see the geologist pointing at the fault there, which has a centimeter scale of offset. In the upper right, you can see a core from offshore Santa Barbara, where the scale of slip on that particular fault is something on the order of maybe ½ centimeter. So how do we decide how much slip we get for what size fault? Well, this is a plot that shows the scaling of the maximum slip on a fault to the fault size. And for purposes of today, the fault size we're going to say is basically the length of the fault. The y-axis on this plot is indicating the maximum slip in meters. The x-axis is the length of the fault, also in meters. And you can see these dashed lines, which are basically the slope, 0.001 to 1. So basically, if the curve is equal to 1, that means I get a meter of slip on a meter-long fault. You can see there's virtually no faults that show that magnitude of slip. Typically, what we see, most of the data is between the 0.1 and 0.01 dashed line, which means that if we have a fault that's 100 meters long, typically the maximum amount of slip we observe in outcrops that we see these faults at the surface is on the order of maybe 1 to 10 meters. So maybe something on the order of 1% is the maximum slip we get based on the size of the fault, 1% of the size of the fault. So in order to use that, then we say, okay, well, what kind of fault causes what kind of earthquake? Well, I've got a chart here. It's kind of a little bit busy, but basically I've got an equation which is called the scalar seismic moment. This is a way for us to calculate magnitudes of faults based on their dimensions. This equation is m naught, that's written up there in the corner, is equal to g, which is the elastic property of the rock, the shear modulus. A is the area of the fault, and d is the amount of slip. We can take that from our geologic example of faults where we have the dimensions, so we can convert that with the equation on the right into the Richter magnitude scale. And that equation shows how you can make that calculation. So let's just look at a fault like that outcrop in California where the slip is on the order of a centimeter. So this scale is 0.008 meters. It would be 8 millimeters. If we assume that that's 1% of the dimension of the fault, then the size, the length of the fault is almost a meter. That would calculate out to be a -1 magnitude earthquake. That's kind of the typical sort of magnitude we get in hydraulic fracturing. Some of the felt earthquakes that people have been talking about in the news media in Texas and Oklahoma are more like a scale where we have something on the order of almost a meter of slip. That would imply that the fault patch is 80 meters in size. And this is basically not necessarily the entire fault is that big, but the area that has actually slipped is that big. That would give us a magnitude 3 fault on the Richter scale. So that gives you an idea of how much slip and how big the faults are for these kinds of earthquakes. So the magnitude 3 is what people see in induced earthquakes where we feel them. The -1 is kind of a typical hydraulic fracturing earthquake. So this is a chart from the National Academy's report, and this shows maximum induced earthquake magnitude on the y-axis and volume injected or extracted in millions of cubic meters on the x-axis. And what they show, what I'm going to focus on here, is in the middle, these are basically injection wells. And the implication is here, roughly, just very grossly, the amount of fluid you're moving around can increase the magnitude of the fault you might induce. But it's in this middle ground where these injection wells are, it seems like the correlation is fairly weak, but there seems to be some relationship. Hydraulic fracturing events are basically much smaller magnitude earthquakes because they're much smaller volume injections compared to a 24-hour-a-day, 7-day-a-week injection well. Okay, so finally I want to look at this. How do we decide whether an earthquake is big or not? And I just talked to you about the magnitudes that we might get on the Richter scale. the thing that actually causes damage and that people feel is the ground acceleration. And so this is a chart that the USGS has put out called the Mercalli scale. And this is basically ratings of damage and perceived shaking. And you can see here in the there's the instrumental intensity. Basically, these stages are from 1 to 10, and I've just circled the magnitude, Mercalli magnitude 6 and 7 here to show that the ground acceleration is on the order of 0.2 g, so 0.2 times gravity. Okay, that level we'll look at in the next slide. But a 0.2 g is something that if you were looking at whether you perceive this, it would be very strong, strong to very strong. The damage, though, would be light to moderate, like that picture that Cliff showed where somebody's chimney had been knocked down. If you take this then to how far away would an earthquake shake, we look at this chart here, which is ground acceleration in the y-axis in magnitudes of gravity, so constant times g versus distance in kilometers. And if we take that magnitude 3 earthquake, or magnitude 4.5, which would be one of the larger induced earthquakes, 0.1 g, which would certainly be felt by people, it's a borderline for strong shaking and light damage, you could feel that up to 12 kilometers away, or it would be 0.1 g up to 12 kilometers away from a magnitude 4.5 fault. If we wanted to get that stronger shaking, 0.2 g, basically you can see that that would only occur immediately above the fault. So the area affected by an earthquake, you can see in that my top bullet here, depends on the magnitude of the earthquake, the depth of the earthquake, and the distance that structures are away from the earthquake. So earthquakes downtown in Basel, Switzerland would upset people very greatly because they're sitting right on top of it. If one of these earthquakes occurred out in the middle of nowhere in the countryside, it wouldn't be noticed that much. The other thing that affects shaking, which I haven't included in this slide, is basically what is the rock like or the soil like in an area. So hard rock country would work differently than an area where the soil is very thick. Okay, so one last thing about just the geology of this problem, and one of the things is that sometimes faults slip and don't cause any sort of earthquake. And we know, you may have heard this, there's areas on the San Andreas Fault that slip aseismically or slip brittly. I stuck this picture in here partly because there's a graduate of our department, Russell Parker, there for scale in the foreground, but you can see this particular slide. I've got a fault that's got some shale that's been smeared through the fault, and there's been a bunch of ductile deformation here, not such a brittle fault. So slip on the order of a couple meters, but this probably wouldn't have generated any sort of seismic activity. And people know that, for instance, in Houston, due to water extraction for drinking water and things like that, there's a fair amount of fault slip going on in the unconsolidated sediment that doesn't cause earthquakes. Okay, so we need to have reasonably brittle rock in order to get earthquakes to be generated by fault slip. So just a little bit about the mechanics then. And this is something some of you I saw on the list there have been sat through my geomechanics class, but the way we look at this and do the prediction part of earthquakes would be to say, let's go to the laboratory. We've got a core sample. We put some confining stress on it. That'll be the x-axis on my plot. And I call that S3, which is the minimum stress. Most of you would treat that as SH min, which is the frac gradient stress, minus the pore pressure. So when we're looking at shear failure, we always look at the effective stress, which is our earth stress minus pore pressure. In the laboratory, we'd apply an axial stress, which is typically the vertical stress in the field. That's S1 minus P on the y-axis. And then we would load this sample until it failed. So we'd go to a particular confining stress, and you see that arrow, and we'd plot a point in the laboratory that would show when that failed, at what axial stress did that fail at for a particular confining stress. And we would do this multiple times and create a plot, which is the failure envelope. Now, why is this important? This is important if we want to try and say something about when fractures would form or when faults would slip in the field. So the slope of that line is part of the envelope and the y-intercept, and we can basically write down an equation that describes the failure behavior of rock in the subsurface. And I'm not going to dwell on the equation there, but you can see I have it written out. It's simply just a linear envelope, which we use terms of stress, and the mu on the term of the equation I just showed you is the friction coefficient, and that UCS, the y-intercept, is what we called unconfined compressive strength. So if we're in a stress state that goes above that red envelope line, then we would be in shear failure. If we're below the line, we would be shear stable. So let's apply this to the subsurface. Well, the first thing about the subsurface is we think there are a lot of pre-existing faults, so that unconfined compressive strength in the Earth's crust typically is presumed to be 0. And we start out at some initial stress state, which would be stable. Let's say we're starting to inject into a reservoir. If we inject in that reservoir, we change the pore pressure, and you notice both of these y-axis and x-axis have pore pressure terms in them, so as we inject, we have an injection path that could lead us to intersect that blue line, which is a failure envelope, and cause failure, and cause a fault to slip, and possibly generate an earthquake. So that's how an injection well might cause this to happen. If we went the other direction for this particular reservoir, which would be depletion, where we decrease the pore pressure, that would be a stable path. Now, it turns out the slope of this line actually depends on the rock. So in some situations, in some reservoirs, in rare cases, the injection path is actually stable, and it's the production path that leads us to shear failure. The slope of this line is basically a thing that depends on the rock properties and the poroelastic behavior of the reservoir. Other mechanisms that can lead to depletion in induced seismicity are basically related to the geometry of our reservoir. You can see this picture from a paper by Siegel. That gray blob is a reservoir in the subsurface for a vertical cross-section, and as you produce the reservoir, it shrinks, which actually changes the stress field around the reservoir and can induce faulting in this variety of possible scenarios shown in Siegel's diagram. Now again, those wouldn't cause earthquakes unless the rock were sufficiently brittle and the stresses were sufficiently high. Just to kind of wrap up here, so let's talk about two last things. What about hydraulic fracturing? Cliff mentioned that hydraulic fracturing is unlikely to cause big felt earthquakes. What does the data look like? This is data from a paper by Warpinski, and they're basically looked at thousands of frac jobs, the microseismic imaging of thousands of frac jobs. The upper left diagram, which is basically magnitude versus depth, it's a little bit hard to see here, but you can see the maximum size earthquake is about a magnitude of 1/2. Most of the earthquakes, these little red dots, that are caused down to a depth of 9,000 feet are magnitude -1 on average. Increasing the rate for the frac job, you see in the lower left corner, even up to 120 barrels a minute for the data set, the maximum magnitude is something on the order of magnitude 0. The volume injected for frac jobs now, not for injection volumes, injection wells, again, it doesn't seem to correlate well with injection volume. So essentially what we're saying is that hydraulic fractures, the magnitude is almost always less than 1. Okay, so one last thing just before I wrap up here. What are we doing at Texas to address this problem? Well, Cliff and I are actually part of a RIPSI program, a federally funded program where we're doing some research. And Cliff is working on the seismic interpretation and seismic monitoring side. I'm working on some of the fluid flow modeling and predictive modeling. And I just want to show you one of the things we're doing. We've actually collected data on all of the injection wells throughout the Fort Worth Basin. This is a picture of the Fort Worth Basin. You can see Dallas over there on the right. And we've discretized that in a reservoir simulator, and we've actually calculated the pressure distribution through time from all the injection wells that are out there. And you can see basically there's this big green area towards the south in Johnson and Hood County. That's an area where, based on the injection history we've been able to put together, maybe something on the order of 50 psi increase in pore pressure. All those red triangles up in the middle of the diagram near Azle are locations of earthquakes. You can see that there are some earthquakes in an area of increased pressure. One of the big challenges for prediction is exemplified by this diagram, though. There's broad areas that have increase in pore pressure. Only very, very few places actually have earthquakes. And the question is, why do we get earthquakes in some places and not in others? Every injection well, 99.9% of injection wells don't cause any problems. Why do the very few actually cause problems? And so that's part of the research that we're working on. So just to summarize then, I think, if you look at all the presentation we went through today, there's a strong case that oil and gas activities can induce or have induced a small number of felt earthquakes. Seismic activity is related to very, very few of the million active wells in the United States. This NRC report states that the activities that pose some risk are typically continuous injection or other activities, are unlikely to induce felt quakes. And then the idea that we have something, we do know something about how the physics works Risk mitigation is possible. Things like reducing the rate or limiting the pressure in injection wells can help us through that. So I think there's a lot of work that we can do, and this is a problem that is clearly one that is available for engineering and science application for risk mitigation.
All right, thank you very much, John. This is Mark McClure again, and I will be moderating the Q&A session. So I'd like to remind everyone that if you have a question you'd like to ask, please type it into the chat box on the left side of your screen, and then I will be reading those questions and then repeating them back and asking John and Cliff. So let's see. There's one good question that just came up. That's a good one to start off with. Do induced earthquakes associate, one, with the rate of injection, and two, with the injection pressure, and then also three, certainly with the total volume injected? So either one of you can answer.
Mark, I'll take that one. There's a lot we don't understand about induced earthquakes, so you can't make any statement that's 100% true. However, almost all the induced earthquakes that we find are in areas where there's relatively high injection volumes. As if in Johnson County, for example, we looked at induced earthquakes, and all the induced earthquakes were within a couple kilometers of injection wells that had more than 150,000 gallons a month injected at some point. There's been a proposal that the total volume injected can tell you something about the maximum possible size induced earthquake. However, that thing hasn't been established, but there has been a suggestion that that's true.
And I'll just add one thing to that. Another thing that people have attributed to places that are more likely to cause earthquakes is basically proximity to the basement rock. And I'll just add one thing to that. Another thing that people have attributed to places that are more likely to cause earthquakes is basically proximity to the basement rock and where there might be large faults around too. And this idea of injecting more volume would basically allow you to pressurize a larger area of a fault. So that might indicate higher risk for higher magnitude quakes. But again, it's a rare.
So along that same line, there was actually a pretty interesting question asking, what about an aggregate effect? So if you do a ton of frac jobs, maybe you should add them all up and count them as one thing. You know, do they all, even if they're all kind of spatially dispersed, is there kind of an aggregate effect that kind of regionally could affect induced seismic hazard?
More likely to.
Well, as I said, there is almost no association between frac jobs and earthquakes. In fact, we don't know exactly why some injection wells cause earthquakes, but we speculate that they only cause earthquakes as if there is a fault within a kilometer or two, and that the fault is stressed and suitably oriented. And so one reason that we speculate that the reason some injection wells cause earthquakes and others don't is the ones that don't cause earthquakes aren't near faults that are suitably oriented, that are stressed. But again, it's not the fracking, it's the injection that's the problem.
And just to add one more thing about the topic of aggregate effects, even though people talk about millions of gallons injected in frac jobs and horizontal wells, that's still really small volume over time compared to these wastewater injection wells. So even the aggregate volume of all the frac jobs is still a pretty small thing compared to one of these high volume injection wells.
All right, so you guys both touched on this already, but there were several questions about it, so I'll give you one more opportunity to expound a little more. There were several questions asking, how are we sure that it's really the wastewater disposal causing earthquakes and that the hydraulic fracturing is not apparently the main culprit? So you guys already talked about that, but if you have any other comments.
Just to add.
Well, let's see, I'd say a couple things. One is from just pure empirical association is there are millions of frac jobs, and most of them don't have earthquakes near them. There's thousands of injection wells, and some of them do have earthquakes near them. So it's just pure empirical arguments. In terms of cause, you have to be a little bit careful. Just because you're injecting and have an earthquake, you can never prove 100% that the injection is causing the earthquake. I sometimes make the analogy about smoking and lung cancer. When my mom died, she had cancer in her lungs, but she never smoked. Other people smoke all their lives and never get cancer. The same thing is true that you can be injecting and get an earthquake, but you can't prove 100% that the injection caused the earthquake. Like the lung cancer, you can do statistics, and you can show that there were 100 wells, and that 12 of them the injection must have caused earthquakes, but you don't know which ones. So.
And this is John. I'll just add one thing to that. There was an experiment that was done by oil companies after the Rocky Mountain Arsenal earthquake, and they actually went to the oil field called Rangeley Field in Colorado, and they actually did injections until they caused earthquakes. So they actually did a field experiment to try and reproduce this. So if you're interested in that, you could Google Rangeley Field, and I think it's a science paper from the late 1960s, early 1970s. But some oil companies actually went out with the USGS and tested this problem.
Yeah, and that Rangeley was really cool because they intentionally increased injection rate. They saw more seismicity, then they backed off and it went down, and they fluctuated the rate, and they actually watched seismicity track the fluctuations of injection. All right, so another question. How does the soft sediment or the shallow Earth surface affect the magnitude of the induced events?
I'll take a stab at that. This is John. I think the magnitude of the quake itself is actually largely determined by the subsurface fault conditions and stress. The amount of shaking you get would be influenced by the amount of sediment and things at the surface. So for instance, areas that have soils that can liquefy, smaller quakes can cause more damage than in areas that have more solid base. But I'll pass it over to Cliff to add anything that he wants to add to that.
Well, for earthquakes generally, earthquakes that are close, an earthquake of a given magnitude that's closer to the surface is going to cause more shaking on the surface. And also, in terms of the amount of shaking, it turns out that's hugely dependent on the kind of materials near the surface. The worst possible situation for an earthquake is where you have unconsolidated sediment near the surface, and so you can get shaking that's many times more than you would on a hard rock. Intuitively, you would think that earthquake waves would be stronger through hard rock, but that's not true. And in fact, again, independent of induced earthquakes, if you look at some of the worst earthquake disasters in the world, they invariably occur either on old lake beds, as in Mexico City in Nicaragua, or they occur on man-made land, as the San Francisco earthquake, the Marina District was reclaimed land. And so the one reason they had such horrible damage there was because they had these soft sediments that the reverberations amplify the earthquake waves.
All right, thanks. Another question for either of you guys. So if we think that wastewater disposal is potentially hazardous, are there alternatives to disposing the wastewater?
Well, I'll take that, I guess. There are certainly alternatives. For example, as I mentioned, you could take the material and treat it like we do sewage. And in fact, I suspect, given how valuable water is in the South, that if we talk to our grandchildren in 50 years, they would say, "You mean you just pumped it back in the ground?" Because that water is so valuable. Now, that said, one has to be a little bit careful, because for alternative strategies, they're also, if you take something like the frac fluids and start treating, you have to transport them. I mean, you're dealing with chemical processes, and the hazardous minerals and mercury and so on that are in the wastewater, people get exposed to that too. So it isn't just so simple that injection is dangerous and bad, and treating it some other way is good.
And this is John's. A couple of technologies that are being used in fracking right now are recycling. So it's actually recycling and pumping it back into another frac job, and that's done significantly in Pennsylvania. The other thing people are looking at is using something other than water, which there's people that use propane or other kinds of fluids, hydrocarbon fluids, for injection. And so then we wouldn't be disposing of those after the fact. But there had been a history of some things being run through municipal water treatment plants, and like in Pennsylvania they had some history of that, and those plants couldn't handle get everything out of the water that they needed to. So.
All right, thanks. Another question is there a temperature role? So we've mainly talked about changes in pore pressure. Is temperature potentially an influence?
I can just say something. One thing about that. There is, when we're injecting from the surface cold water into the hot subsurface, and I think this happens, you might comment on geothermal wells, Mark. You do get some shrinkage, and that shrinkage can actually change the stress state such that faults would be induced. People actually use that in injection wells to try and enhance fracturing of injection wells. The cold temperature will actually contract the rock and make it easier to break the rock or open fractures. There is...
Yeah, I don't know much about the temperature of the fluids that are being pumped in there. Certainly, in terms of the physics of the rock, the physics depends hugely on temperature. That is, so one reason that if we look at injection in 10 different places, we find 8 different behaviors, is that the kind of rock and the temperature of the rock can be very...
All right, thanks. Yeah, I would also add to that. I think during the shorter period injection, the region of temperature perturbation is pretty small and it's not a major impact, but definitely during long-term injection, it's capable of being important. Definitely, we just got a question, is there a difference between induced events in geothermal and wastewater disposal? So in geothermal energy, sometimes just wells are drilled and you produce fluid, but sometimes there's long-term fluid injection in geothermal reservoirs, and that is absolutely associated with seismicity. So we didn't talk about induced seismicity for geothermal, but it's absolutely an issue there. And a part of that is that the cooling of the rock caused by the fluid injection creates a contraction, and that has an effect similar to fluid production, and that is capable of inducing seismicity, and that's well documented. Do you guys have any other comments on that? Okay. Sorry for stealing your question. One other question, stress regime. So normal stress regime, strike slip, and so on. Does that seem to have an impact?
I'm sure it has an impact, but there are induced earthquakes in both kinds, well, in all 3 kinds of stress regimes. So it's not a simple answer like, yeah, all the earthquakes that are induced are normal. That's not true. There's all 3 kinds.
This is John. One of the things you might say is we're perhaps more likely to locate some of our injection wells in large sedimentary basins in the central part of the U.S. where it tends to be more towards normal faulting to strike slip faulting regime. So I think in the hard rock thrusting areas we maybe just don't have as many injection wells there. So it's basically a choice of where we put the wells.
All right, we got a question. I've seen this question many times. People always ask this question. How about the idea that we could intentionally inject into faults, causing small events, and maybe that would decrease the probability of a larger event?
Well, this is actually a brilliant suggestion, and it's a suggestion that's so brilliant that it's been thought of hundreds and thousands of times. That is, after the Denver earthquakes in the 1960s, people actually proposed that maybe we could control seismicity in California by injecting along the San Andreas Fault. The idea, instead of getting magnitude 8 earthquakes every 100 years or so, you could get millions of magnitude 3 earthquakes. And that's a good thing because earthquakes are like thunderstorms. A magnitude 3 is kind of fun. It wakes people up. The next day they say, did you feel it, or did anything fall off your shelf? Magnitude 8s are not fun. It's like a thunderstorm, there's lightning, everybody wakes up the next day and talks about it. A hurricane with 200-mile-an-hour winds isn't fun. However, it's never been considered practical to control faults like the San Andreas this way. And I suspect if you were injecting along a fault and a magnitude 8 happened, that your great-grandchildren would still be sued in the courts after 50 years.
All right, another good question here. Do you have to have a pre-existing fault to get induced seismicity?
This is John. I'll just comment. It seems like from what I've read in the literature that people are like Cliff said, we don't totally understand what's going on, but it seems like the seismicity that we get in felt earthquakes is almost exclusively attributed to pre-existing faults being lubricated or pressurized by some sort of process.
Yeah, I would agree with John in the following sense. First of all, the vast majority of induced earthquakes, we have no idea whether there's a fault nearby. We don't have an image of the subsurface. However, in those situations where we have good images of the subsurface, all or virtually all of them, you find a fault. And so you can either say, well, that's evidence that the induced earthquakes only occur where there's faults. A cynic would say, if you look hard at the subsurface, almost everywhere you'll find faults. But right now, I would say most people find it such an appealing model that earthquakes only occur on pre-existing faults that they would say it's true, even though we don't have strong evidence for it.
All right. All right, so it's 1 o'clock, so we're out of time. Thank you, everyone, for the very excellent questions. Cliff, John, and I have put up our emails. Let me switch over to the next slide here. All right, so here's our emails. So please feel free to email any of the three of us to ask follow-up questions directly. Also, if you have any general feedback about the overall presentation, you can email the CPGE email address at the bottom of this slide right now. Now, if you signed up to receive CEU credits, please go to the online survey link shown here at the top of the page to verify your participation in the webinar, and we'll leave this slide up for several minutes. Next semester, we will bring you our Knowledge Pipeline webinar on the topic of gas hydrates. We will be sending out information on speakers and times throughout the newsletter. Thanks for signing on today. This webinar is brought to you by the Center for Petroleum and Geosystems Engineering. Thanks again and have a great day. Thanks again and have a great day.